Welcome back to lecture 18.2, where we're going to apply our Clausius theorem to understand reversibility, versus irreversibility. Okay, so remember, let's start by restating our Clausius theorem, or let's call it the Clausius inequality, because I just think that's fun. So the Clausius inequality was that around a closed loop, dq over t was always less than or equal to 0. And that equal was going to be for reversible and the less than for irreversible processes. Okay? So let's imagine this situation on a PV diagram where I'm going to go from one state A to another state B. And what I want to do is have, so let's say, imagine two processes. One reversible, one is reversible and one is not. Okay, so imagine some process like this, which I'm going to call my reversible process. And one process, let's say, which is some really weird functional form, and that's going to be irreversible. Okay, so I want to go from A to B along the irreversible path, and then I want to go from B to A along the reversible one. Okay, and let's calculate what happens for Clausius inequality in this condition. So it's a closed loop, so we can apply this, right? So if we apply Clausius as an inequality, we can say this is going to be the integral from A to B along the irreversible path plus the integral from B to A along the reversible path. Okay, so we have some part which is irreversible, so we know we're going to have the inequality. Okay, so that's going to be less than 0. Okay, so we can flip the sign of this and imagine it going the opposite path. So let's call this the integral from A to B dq of t along the irreversible path plus minus the integral from A to B along the reversible path. Okay, so we're going to just move that one to the other side, the irreversible, right? So we're going to say that the integral from A to B of dq over t irreversible is always less than A to B dq over t of the reversible path. But if it's reversible, we know that for a reversible process that this can be taken to be an exact differential, right, and turned into our entropy. So dq over t or an irreversible path, is less than the integral from a to b ds. Now let's just continue to point out that this is along a reversible path, which means that this is simply equal to SB minus S of A, right? Because this is a state function. And so we can say that this change in entropy we have, delta S, right? Or we can really say that ds is not equal to dq over t for an irreversible path or process. Right? This was ds. This was our delta S, right? And so you can see that this is not true. This is why we're careful when we have to write dq over t versus when we write ds. Okay? Or another way to might say it really is ds is a state function, right? And so ds is always an exact differential. So maybe what we should really write is that it's the heat which might be different, right? dq is what might be different between a reversible and irreversible path. Okay? Okay, so imagine though an isolated process. So where we're doing this entirely inside of some system where no heat can come in or out, right? Completely isolated from the rest of the world. Then dq is equal to 0, right? Because q is equal to 0. And so then you can see that in our equality, 0, right, was less than or equal to SB minus SA. And right, and again, the inequality is only for a irreversible, and the equality is for a reversible. Sorry. So if irreversible, then SB is greater than SA. And if reversible, then SB equals SA. You can see that's exactly consistent with our statement of the second law we made last time, right? Which said that if it's irreversible, the entropy increases, right, going from A to B. But if it's irreversible, it's constant. So we can see Clausius's inequality is exactly consistent with that definition of the second law. Okay, so imagine that we went from A to B, and then we went back along B to A. Okay? Actually, let's pause here, and then we'll consider that case separately as another section where we call it about isolated systems.